Okay, so we talked about matrix equations last week, and one big use of matrices is it's an easy way to solve a system of equations. All right, and so we've learned a bunch of different techniques for solving systems of equations: substitution, elimination, Cramer's rule, graphing. Well, we're going to learn how to do it with matrices. And to solve it with matrices, we need to make a matrix equation. And we already used these, right, on Thursday. We've used matrix equations, and but specifically for solving a system of equations, it's going to have a specific form where we're going to have three matrices in this equation. The first one is going to be made up of all the coefficients, which you all know what that is, right? The coefficients, those are all just like the numbers in front of the variables. Then you're going to have a variable matrix. Well, that's pretty straightforward. That's just going to be the matrix with your variables in it. And finally, it's going to be equal to the constant matrix. So if you recall the constants of an equation, a constant is just like a number that doesn't have a variable next to it, right? It's just the numbers that are all by themselves. And so that's going to be what's in the matrix on the right. So this is kind of a similar setup to Cramer's rule in a way, but we've got this variable matrix here instead. So here's the general setup that we're going to be creating, okay? So we're going to take a system of equations today, and we're going to write it in this form with the coefficient matrix times this variable matrix, and it's going to equal the constant matrix. Then we're going to use our matrix operations to solve it for that variable matrix. All right? Let's see what that looks like. So first off, just like in Cramer's rule, we want the equations to be written in standard form. So just a refresher for standard form, that's what we've got over here on the left. All right, you've got x's and then y's equals the constants. All right, so that's standard form. And once you've got that set up, then you're basically going to convert the numbers into two different matrices. And if you see, they match up pretty nicely. We've got the coefficients on the left, 7, 5, 3, negative 2. That's right here, 7, 5, 3, negative 2. Okay, so that would be the coefficient matrix. It's literally just a matrix of the four coefficients of your variables. On the right, the 3 and the 22, well, those don't have variables next to them, so those are called constants because they don't change, they don't vary. 3 is always 3, 22 is always 22. And so those then become the constant matrix. So you just take your two groups of numbers, basically, and you put each one of them into a matrix. What do you think? Can we do this so far? Nothing too tricky? Now there's one more matrix we need. Do you remember what that third one was called? Variable matrix. Yes, that's right. Good job, class. The variable matrix. And so that variable matrix goes right in the middle. And this is what our matrix equation is going to look like. So this is how you want to convert a system of equations into a matrix equation. So we've got the coefficient matrix on the left, and the order is important. We've got to have these in the right order. Coefficient matrix comes first. It's going to be multiplied by the variable matrix. And your variable matrix is going to be just x over y, just a 2 by 1 matrix. And it's going to equal the constant matrix. And that's it. Now, I know you're all probably wondering, Mr. Wojcik, why do we set it up this way? That seems totally weird. It doesn't look like an equation. But check this out. This is actually kind of cool. I know, you're like, math, cool, come on, get real. No, but watch this. If I were to multiply these, which we're not, because ultimately our goal to solve an equation is to figure out what the variables should be. But check it out. If we did multiply these together, rows times columns, you know how we always multiply like the first with the first, second with the second? We'd get 7x plus 5y. And isn't that first equation, right? It was 7x plus 5y. Isn't that kind of cool? And then we did the second row. You get a 3x plus negative 2y, and that was like the second equation. Yeah, it's awesome, right? Math. It's beautiful. For those of you who see what happened there, good job. And then it equals the 3 over 22, the constants. Now, if we were going to solve this equation, we want to get the x and y by itself. What will we need to do? Well, to solve for a variable, we want to cancel something out, right? You cancel out the other stuff. So we would need a way to cancel this out. And do we know a way to cancel out a matrix? Yeah, an inverse, right? Multiplied by the inverse matrix. That's what we're going to be doing to solve. So first, I want you to practice. I want you to write this system of equations, make that a little bigger for you, as a matrix equation, okay? So just what we started off today with so far. Take those two equations and remember what form they need to be written in. Now, standard form I said was x and y. If there's different variables, just put them alphabetically, same idea, all right? So do j plus k equals the constant. So rewrite them in standard form. And then I want you to convert those equations from standard form into a matrix equation. All right, so when I say matrix equation, this is what I'm talking about, one of these, okay? So this is what I want your final answer to look like, that matrix equation that you just wrote down with the three matrices. So write in standard form, then convert to a matrix equation. All right, so this first one, we've got the j already on the left. We're going to bring the k over just by adding it. So this is going to become 6j plus 3k equals 5. That second one, technically, this is kind of already in standard form, right? J and k are on one side, the constant's on the other side. We're just going to flip-flop it. And with the equations, you're allowed to do that, right? You can say like 2 plus 3 equals 5 or 5 equals 2 plus 3. So I'm just going to swing that second one from left to right. So I'll put that 3j plus 2k on the left and 10 on the right. So those are our two equations in standard form. You got j, k equals constant, just like you would have x plus y equals constant. And now we need to make our three matrices. So the first matrix It's called our coefficient matrix. That comes from the three coefficients, or the four coefficients, those numbers in front of all the variables. In this case, we've got 6, 3, 3, and 2. It's going to be multiplied by the variable matrix. So the variable matrix, that's just going to be whatever your variables are in that same order from left to right. That'll be the same order from top to bottom. So times JK, and then it's going to equal the constant matrix. So the constants, those are the numbers that don't have a variable, the numbers that are just by themselves, hanging out on the right. So that's 5 and 10. So right there is our matrix equation. Did anyone have this written down, just out of curiosity? Okay. Awesome. Good deal. So you can all set up a matrix equation. It's the first step. You got this. Any questions on how I set that up, though? From anyone who's not sure
I
why?
had everything flipped besides the variables. Does that matter?
One more time?
I had everything flipped, like the 6 and 3 were on the bottom, and then the 10 and 5 were flipped.
Oh, that's totally fine. Yeah, so if your equations, if you had the top one, like basically if these equations were flip-flopped, then these rows would also be flip-flopped, and that is 100% okay. It's a good
All
question.
right.
Yep, as long as if you flip these ones, you would have to flip these as well. Then that's fine. But then you still should have J on top and K on bottom. But yeah, you could have those two lines switched. Makes no difference. Good question. Whoops. Okay. All right, so here's what we're doing. If you recall from last week, we wanted to solve an equation with a matrix, and we had to cancel out a matrix. And so we had to use something called the inverse. And here's what it's going to look like. I'm going to show you like technically what we're doing first, but then what's the actual calculation going to be. So we're solving for variables. So we're solving for the variable matrix, meaning I want to get this matrix all by itself. So I have to cancel out the other stuff on the same side of the equal sign as that variable matrix. So I need to cancel out the coefficient matrix. And to cancel out a matrix, we multiply by its inverse. So if we call this matrix A, I need to multiply it by A inverse. So let's go ahead and practice a skill from last week. I want all of you to calculate A inverse right now for me. Write down the inverse of the coefficient matrix. Let's see if you remember that skill from Thursday. Hopefully you practiced it over the weekend on your homework assignment. So remember, there's two parts to an inverse matrix. There's the fraction out in front. Then there's that same matrix where you kind of shuffle around all the values. Look at your notes from last class. So an inverse matrix, you need to do two things. First, the determinant. So to calculate the determinant, take one diagonal and you subtract the other diagonal. So in this case, we got negative 29. Anyone else get negative 29 for determinant? Okay, nice, nice. For your inverse matrix, you take 1 over that number. And then inside the square brackets for this inverse matrix, you do two things. We swap the locations of the first element and the last element. So negative 2 is going to go in that first spot, 7 is going to go in that last spot. And then you switch the signs of those other two elements. So positive 5 becomes negative 5, positive 3 becomes negative 3. It's important to note that you don't actually switch the locations of those two. They stay put. You're just changing their signs. So for two elements, you flip their positions. The other two elements, you flip their signs, but you don't do both things. You don't flip a number's position and flip that number's sign. So that's the inverse matrix. We would take this and multiply it by that green matrix in the upper left to cancel it out. So I'd take this A inverse matrix and I'd multiply that by this green matrix. Now, should we actually spend time right now to calculate what that's going to equal if I multiply A inverse times A? We should not. Because we know that any matrix times its inverse just cancels it out. That's why we multiplied by the inverse. We wanted to cancel it out. Because if I cancel out that matrix, look what we're left with on the left side is just the variable matrix. That's what we're looking for. That's our goal, to solve for this equation, to solve for that unknown quantity. So I don't need to bother multiplying on the left by this A inverse. But because it is an equation, we have to keep it balanced. So if I do some operation on one side, I've got to do that same operation on the other side. So I multiplied the left by A inverse. I've got to multiply the right side of the equation by A inverse. But here's the thing. I can multiply by A inverse on the right side of this constant matrix, or I could multiply A inverse on the left side of that matrix. Now, this is a new concept. Up to this point in your education, the side with which you multiplied two things did not matter, right? 2 times 3 is the same as 3 times 2. Makes no difference. With matrices, however, it matters. Multiplication is not commutative any longer. In fact, one of these ways, you physically can't multiply the two matrices together because like the rows and columns thing doesn't line up. Remember how you have to have those inner dimensions matching in order to multiply? So here's the general concept that you're doing. This right here is our matrix equation. A times B equals C. Coefficient matrix times the variable matrix equals the constant matrix. Now this is just an illustration to show you what's going on. To cancel out matrix A, we multiply by A inverse. Now, we chose to put like A inverse on the left of A. We had to because matrix B was on the right side of A. I couldn't put this like in between. I could not squeeze this A inverse in between A and B. You're not allowed. If there's already a matrix next to it, you can't squeeze a matrix in between them. So when we multiplied by A inverse, you're basically looking at the calculation here. And whichever matrix you want to cancel out, you multiply by its inverse on whichever side is open, like whichever side doesn't have a matrix next to it already. So in this case, if I wanted to cancel out matrix A, I'd have to multiply by A inverse on the left, because the left side of matrix A is open. There's nothing there. And if I multiply A inverse on the left side on one side of my equation, you have to multiply on the left side on the other side of your equation. And that's the weird part, because usually whenever you have a constant over here, you just multiply it here on the right, just because there's room to write it. But we can't do that because A inverse is being multiplied on the left. It's got to go on the left on both sides of the equation. And that's the weird thing. Now with these matrices, it'll be a little easier, because if you did try to multiply A inverse on the right side of C, you wouldn't have the rows and columns matching up. It wouldn't work. This way, it does work. So A inverse times C. So basically, whichever side you multiply a matrix by to cancel it out, you've got to multiply it on that same side on the other side of the equation. Which is crazy. I know. Oops. So, over here on the right side, that blue constant matrix needs to be multiplied by A inverse. Since on the left, A inverse got multiplied on the left, I've got to multiply A inverse on the left side of this constant matrix as well. So we can't put it on the right side. So my calculation, basically, I'm going to take that A inverse times the constant matrix. And this is what we're going to actually calculate right now. We're going to actually multiply these matrices together. And so, in essence, that's what my note at the top here was. You have to multiply just the coefficient matrix inverse by the constant matrix in that order. And as long as you set up your system of equations this way and you write out your matrix equation the same exact way with the coefficient matrix times the variable matrix equals the constant matrix, you don't have to think about which side is this going to go on. It's always going to be this setup. This is the only calculation you actually have to do. It's the inverse of the coefficient matrix times the constant matrix. And that'll be it for every single system of equations by matrices. So when you're multiplying, remember, we're going to leave that fraction out in front for now while I multiply my matrices. After we've multiplied them, then we'll bring that negative 29 inside to divide each number by it, just to make it easier. When we multiply matrices, we take rows times columns. Multiply the first element times the first element. That's a negative 2 times 3, which is negative 6. Multiply the second element times the second element, which is negative 110, I think. We combine those and get negative 116. Now there are no other columns, so we're going to drop down to the second row. We take the second row times that column. Negative 3 times 3 is negative 9. 7 times 22 is 154. Yeah, thank you. Add those up and get 144. Oops. So now what we have, 1 over negative 29. But when I multiplied these two matrices together, we got negative 116 and positive 144. Yeah, Brady. I meant 5. Thank you. Good catch. Is that better? Right? Thank you. Okay, so that's just from multiplying the two matrices together. Then our last step is just take that negative 29, and you're just going to divide negative 29, divide by negative 29. What do we get? 4 and 5. Positive 4, negative 5. Works out nicely. Now remember, we were solving this equation originally for our variable matrix, for x and y, right here. Guess what, everybody? Here's x and y. Solution to our system of equations is 4, comma, negative 5. All right, if we graph those two lines on the same coordinate plane, they would intersect at that point, 4, negative 5. Now I know what you're thinking. Can't we just use substitution? Yeah, of course you can. But that's great when there's only two equations. A real life application, you're not going to have just two equations. You're going to have 10. All right? You don't want to use substitution for 10 equations. But with the system of equations with matrices, super simple. You put all 10 of those into a matrix equation. And, well, you're not going to calculate the inverse by hand. You're going to use a calculator. And then to get the inverse with a single button press, multiply the inverse times the constant, and there's your solution for all 10 variables. But we're going to practice it on the smaller scope to get you familiar with the process. Pretty awesome, huh? Yes, it is awesome. I'm glad you think so, everybody. All right, so let's do another one of these all together. We're going to solve this system of equations with matrices. So we're going to solve this for x and y. So go ahead and write these two down. If you're feeling confident, go ahead and push onwards on your own. Otherwise, I'm going to walk through all these steps with you. So let's first get these into standard form. All I need to do is bring that 4x over to the left side. And then add that negative 22 to the other side to get that first equation in standard form. The second equation, the y is in front. I'm just going to switch the positions of the x and the y term. 6x plus 4y equals negative 2. All right, so we got standard form. And now we want to just set up that matrix equation. So we're going to start with the coefficient matrix. And it's easy to keep this straight because you just basically start with the numbers on the left become the matrix on the left, And this gets multiplied by the variable matrix, and it equals, and for this constant matrix, the matrix on the right, you just use the numbers on the right. It lines up really nicely. 22 and negative 2. So here's our matrix equation. So the coefficient matrix times the variable matrix equals the constant matrix. Now we want to get the variable matrix here by itself, so I've got to cancel out this matrix on the left. To cancel it out, we multiply by its inverse. And so because there's already a matrix like on the right side of it, its inverse is going to have to go on the left side of it. And so basically those will cancel out. And then over here on the right side, my true calculation is going to be taking A inverse times that constant matrix. That's all I have to figure out. So let's start by writing out the inverse of the coefficient matrix. So I'm going to take that first diagonal, 4 times 4, which is 16, minus the second diagonal, which is negative 12. I get 28. So this inverse matrix, 1 over 28. And then we're going to do the little like rearranging of those 4 elements. Take the first term and the last term, switch their positions. They're both 4 in this case, so that doesn't really matter. And then the negative 2 and the 6, they stay put, but you just change both of their signs. Negative 2 becomes positive 2, positive 6 becomes negative 6. We take that inverse matrix times the constant matrix on the far right. Times 22 and negative 2. All right, so this is the step, the math part right here. Just multiplying these two together. When we multiply matrices, just take the row times the column. 4 times 22 is 88, plus 2 times negative 2 is negative 4. That gives us 84. Then take the second row times that column. Negative 6 times 22, negative 132. Is that right? Negative 132. And then 4 times negative 2 is negative 8. Which gives us a negative 140, I think. Let me know if I'm off. So our last step, take that 1 over the determinant times these two numbers that we just calculated, the 84 and the negative 140, and we're just going to kind of distribute in that 28. So just divide both those numbers by 28, essentially. Divide by 28, divide by 28. What do we get? What is it? 3 and 5. Thank you. So 3 and then a negative 5. So the solution to this system of equations, we write this as an ordered pair. 3 comma negative 5. Questions on any of these steps? I know, it's crazy. It's new. That's why you have to practice it. We're here in school to learn new stuff. All right, one other technique I want to show you. Dun, dun, dun. And this is going to kind of lead into using the graphing calculator to solve them. And so there's one last type of matrix we're going to talk about this year called an augmented matrix. And the augmented matrix, if you look down here, it's really just the combination of your coefficient matrix with your constant matrix. And I've got a dashed line here to kind of separate those matrices from each other, the constants from the variables. That's not actually going to be there on the matrix. You really will just have that one extra column. And so it's called augmented because we're adjusting or changing, altering, combining. Adding in this one little piece to it. So you're still going to write your system of equations out in standard form. But now you're basically going to make one matrix with all the numbers, the coefficients and the constants. But make sure they're in order with all the variables on the left, the constants on the right. Then it will look like this. It won't be a square matrix anymore, right? The rows and columns won't be the same. We're going to have one extra column than row. All right, now what do we do with this augmented matrix? So this will be when we've got 3 equations or more to solve, like these. Okay, so when you're getting to bigger and bigger numbers of systems of equations. So first, I want you to go ahead and take these three equations here, and I want you all to create an augmented matrix from them. Okay, so you're just making a 3x4 matrix just with all the numbers. It's already in standard form for you. Just put all the numbers in a matrix. And that's really it. That's all there is to making an augmented matrix. You all can do this. I know it. Put all the numbers down just in a matrix, just like exactly how you see them. Nice. So since they're both already in all 3 of them are already in standard form, you really are just writing just the numbers. So across the top, coefficient of the x is a 1, coefficient of the y is a 2, coefficient of the z is a 1, and the constant is a 0. You just do that for all 3 lines. So row 2 should be 2, 5, 4, negative 1, 1, negative 1, negative 9, negative 5. All right, when you write these out, if you'd like to put in the dashed line, you can. It's not needed. We are going to be typing this into a calculator eventually, and you're not going to need that dash line. It's not going to show up there on your screen or whatever. So that's your augmented matrix. Dun, 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 dun. But wait a minute, this hasn't solved anything yet. You're right. What do we do with it? Well, don't write this down, okay? Back in the day, before these fancy calculators, here's how you would have to solve these. You can do these row operations to change and reduce the coefficient matrix to the identity matrix. So we look at this left side. I want to try to change it into the identity, right, with the diagonal of all those ones. And how do you do that? Well, it'd be something like you'd take this row and you subtract this row from it and replace it back up here in row 1. I know this is a thing that, like, I actually learned how to do this in high school. It was evil. It was awful. I am not going to make you do this, okay? Because then, like, 1 minus 1 is 0. Oh, no, I don't want that. Never mind. But you try to get things to cancel out. It's stupid. I don't like it. And eventually, whatever you change the whole row by, it's going to be changing these 3 values. And eventually, what those 3 values end up with, that's your solution. So that's the idea behind it. But again, we're not going to do that. Eventually, you rearrange all these by changing those, doing these different row operations, taking 1 row times 2 minus this row or whatever. And you're going to get an augmented matrix is going to look like this. And that last column, 8, -5, and 2, turns out that is the solution to that system of equations. Now, instead of doing all these row operations, this form is called reduced row echelon form, RREF. We only need to know that because that's what the button's called on our calculator that we're going to press to make the calculator do this for us, RREF. All right, so maybe just write down RREF in your notes. That's really the only thing that I want you to get away from these 2 slides. So you're going to type up that augmented matrix. You're going to then put it in reduced row echelon form. But again, you're not going to do it. The calculator is going to do that for you. And your final matrix should look like this. And as long as the left side is the identity matrix, then that last column is your solution to the system of equations. Now, not every system has a solution, right? Sometimes there's no solution to a system of equations, in which case this left side would not be the identity matrix. Okay, so make sure you see that diagonal of 1s and then 0s everywhere else. And if that's so, then that last column is your solution. But yeah, we're going to do this the easy way, obviously. So everybody, grab out your graphing calculator. If you don't have one with you, grab out your Chromebook. All right, for those of you logging in on your Chromebook, if you go to my P-Learning page, just right on the front, right on the main page on the welcome, there is this very first box right here. It says Graphing Calculator app, TI-84, Color Edition. It says click here to get access to this free TI-84 Graphing Calculator app from the Chrome Web Store. So all you need to do is click here. It will take you to the web store that shows this TI-84 Plus Color Edition app. Now, on my computer, because I'm on a desktop, a Windows PC, I cannot download it. And right here, it says not compatible. It doesn't work. On your Chromebook, though, you'll have a button up here that says install or add to Chrome or whatever. Click on that. Let me make sure it's working for you. Yeah, hit launch app, that blue button. Boom. And there it is. It works. And then, yeah, I can hit launch app. There you go. Pretty awesome, huh? By the way, now that you've like installed it or launched it on your Chromebook, to access it again, all you need to do on your Chromebook is press the like the magnifying glass button on the left side of your keyboard. It's like above Shift or whatever, and that will open up all your apps, scroll through them, and this graphing calculator app will now be in there on your Chromebook. All right. So I've got an old school version of it. Mine's not as fancy. I know, it's lame. And that's super small. Let me see if I can make this bigger. No, not that window. Sorry, it's super tiny. Can you guys kind of see that? All right. I'll talk you through it. Okay. So take out your graphing calculator, and we're going to do all this stuff on the graphing calculator. Yeah. If we do put in like a graphing calculator portion, then yes, you'll use this app on it. Sound good? All right, so we're going to enter matrices in our calculator. We're going to do operations with them, find determinants, find inverses, and then get these matrices in a reduced row echelon form. All right, so we're going to go through all that stuff right now. So let me put this just top and center for you. So to use the graphing calculator, first, press the ON button in the lower left. That is on. Good, you got that? Excellent. For regular calculations, you just type things in and hit enter, and that'll calculate stuff for you. Wait, mine's not calculating it. Why not? I think mine just froze. Dun, 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 dun. Why is it thinking? Hang on. Mine's not anywhere near as cool as yours, unfortunately. Yours is way better than mine. So let me see if this will work. Oh man. Let's try this silver edition. No, this should work. This worked earlier. Okay, I got it. I had hit the play button apparently. There we go. 6 times 8 equals woohoo. Okay, I can work technology. All right, so matrices. On the left side of the calculator screen, there should be a little button. In mine, it says it in yellow. It says matrix. Now, for any button on here, if you just press like second and then that button, it should bring up that menu. So everyone, bring up the matrix menu. And then you've got a bunch of matrices here, all in capital letters, A through G, and so on and so forth. You can go up and down and scroll through them all. And initially, you want to enter values into a matrix. And so on the top of the screen, you got names, there's math, go over to edit. And so edit is when you can actually type in values into a matrix. So I'm just going to go to edit and have matrix A here and press enter. At the top of the screen, right now, this is a 1x1 matrix. We're going to enter a 2x2 matrix. So to change the dimensions, that first number is the number of rows. So press 2, hit enter, 2 again, enter. And now you've got this 2x2 matrix that you can enter on your screen. And let's go ahead and do this again with our earlier examples. So let's go back Let's go back to this one. All right, so I'm going to use this matrix for my example here. So this 2 by 2 matrix, I want to enter this coefficient matrix that we used earlier, just to make sure that it works right. So 7, 5, 3, negative 2. All you do is type in the number and then press enter. So C7, then it always goes left to right, just the way we read. So 7, enter, 5, enter, 3, enter. Hey, very, very important, real quick, on your graphing calculator, everybody, the subtraction sign and the negative sign are very, very different, okay? Make sure that if you're just typing in a negative number, use the negative sign that's down on the bottom row, okay? Do not use the subtraction sign if you're writing a negative number. The calculator gets confused. So you have to type in -2, enter. So you should have 7, 5, 3, -2. All right, so we're calling that matrix A. Now we are going to need this constant matrix as well. So we're going to go back to the matrix menu. So press second matrix again. Go over to edit. And you should notice that next to A, there already is 2 by 2 because that's the matrix we just typed in. We don't want to overwrite that. So just go down to matrix B. Press enter. And we want to enter the dimensions of the constant matrix. It's a 2 by 1 matrix. So press 2, enter, 1, enter. We're going to enter these values, 3 and 22. So 3, enter, 22. So then press second matrix again and go back to edit and go down to the next, go to like B and hit enter. And now you can type in an additional matrix. So this is going to be a 2 by 1. Just hit the left arrow key maybe, get you back. There you go. 2 by 1. Then enter the constant matrix. Anyone else having any issues?
No.
Okay, so go to edit, hit enter, and then you enter the dimensions. So do 2 by 2, 2, enter, 2, enter, and now you can type in the values right there. So do the like 7, 5, 3, -2, and just type 7. Hit 7. Oh, and then hit enter, and it automatically jumps to the next spot. Yeah. So everywhere you go over to edit, you can just use your arrow keys on your Chromebook actually.
Okay.
Go over to edit. And then matrix A, hit enter. And now the dimensions are 2 by 2. So press 2, enter, 2, enter. And now you're going to type in those 4 numbers, the 7, 5, 3, -2. Just type it and then hit enter and it'll automatically jump to the next spot.
The -2.
So you probably hit -2 instead of -2.
Ah, yes.
Remember I was saying make sure you keep those separate. Just hit enter right now. Go back to the matrix menu. Go over to edit. Hit enter. Yep, 2 by 2. Just hit enter. Okay, so here don't hit minus. Hit the negative sign for -2. And then enter. Boom, you got it. Now go back to the matrix menu, so second matrix. Go over to edit and go down to matrix B now. Anyone else? We're doing okay? Got it? Good? Good? All right, so now we want to do calculations with these. To do any calculations with a matrix, we have to go back to the main screen. To get there, you just press second and then quit, which is the mode button right next to the second button. That brings us back to our default screen. If there's anything here on this screen, you can just press clear and it will wipe everything from that screen to give you a blank slate to calculate on. Now, we want to take the inverse of this coefficient matrix times this constant matrix. All right. And to do that, we're going to go back to the matrix menu, second matrix, But now instead of editing these, we're going to stay under this first column where it says names. And all you need to do is just use the up and down arrows to select the matrix that we want. Well, we want matrix A, so just press enter. And look at that, it shows up right on this screen. Now, if you want to verify what's in matrix A, I could just hit enter right here, and it shows me those same 4 values that we typed in. Or I could take matrix A, and here's the cool part. Remember all those steps we had to do to find the inverse? Find the determinant, take the 1 over that, switch things around. Well, look on the left side of your calculator. There's a button. It should be that matrix button. It says x to the -1. If you press that, look what shows up on the screen. A to the -1. That is A inverse. If you just hit enter, it gives you, well, all these crazy decimal points. Because remember, it was that like 1 over -29 or whatever. It was a big fraction. If you ever get decimal points and you want to get it into a fraction, very easy way to do that is hitting this math button. All right. If you hit math, the very first option has an arrow and then it says frac. That means it's going to convert whatever was just typed in into fractions. So just hit enter, enter again. Oh, that was a 2. So matrix A inverse math fraction. And check it out. It converted those crazy decimals to these fractions. So this right here, 2 over 29, 5 over 29, 3 over 29, and -7 over 29, that was the inverse matrix that we had calculated by hand for this matrix right here. Now, to solve the system of equations, we would just take so go to the matrix menu, we take matrix A inverse times matrix B. Just like that. A inverse times B. I don't even need to hit multiply because it knows if 2 things are next to each other, it indicates multiplication. You hit enter, and look at that. 4, -5. That's our solution. Okay, that is the easiest way to solve a system of equations by far. Pretty crazy, right? If you go back to the matrix menu, if you go to the right where it says math, there's a bunch of different options in here. That very first one, DET, what do you think that stands for? Yeah, determinant. So I could just hit enter on DET, then it's got an open parenthesis, it needs me to give it a matrix. And so if I go back to that matrix menu, I'm just going to use matrix A here, hit enter, and it gives us that -29 that we calculated by hand, right? Which is easy for a 2x2, but think about for a 3x3 or 4x4 matrix, this is going to be a lot easier to figure out. So that's solving a system of 2x2. Let's try it with that 3x3, that much larger matrix. So I'm going back to example 3 right here. Yeah, so I'm going to show you this reduced row echelon form. We could do the make the matrix equation and take the inverse of the 3x3 times the constant, and that will work. But I'm going to show you this alternate method with this augmented matrix. So we're going to type in this purple matrix exactly like this, okay? So grab your calculator. You can clear the screen if you want. Now, whenever you go to the matrix, there's already that A and B in there. You can easily just write right over those. It doesn't matter what's in there. So I'm going to go over to edit. And even though A already has that 2x2, if I'm not using that anymore, just hit enter. And I'm just going to write my new dimensions, okay? So this new augmented matrix we made had 3 rows and 4 columns. So 3, enter, 4, enter. And I'm just going to type these right across 1 row at a time. On your calculator or on the Chromebook, all you need to do is type the number and then press enter, either on the calculator or on your keyboard. And it automatically will jump to the next number over. And then once it gets to the end of a row, the cursor automatically jumps down to the next row. Make sure for negative numbers, everybody, you must press the negative key, which is on the bottom of your calculator. Do not hit the minus sign, otherwise you'll get an error. And you can use the left and right arrow keys if the matrix goes beyond your screen, like here. I can just scroll to the left and right. All right. Once you've got this typed in, we're going to press second quit to go back to the default calculator screen. And I'm going to go into the matrix menu again. So hit second matrix. And now go over to math, where we found that determinant. I want you to go down until you see RREF. So got it right there. RREF. That stands for reduced row echelon form. You don't really need to know what that means. To me, it means a whole lot of work that I had to do in pre-calculus in high school that I did not enjoy. For you, it's just the button you're going to press to get this done lickety-split. So you go to RREF and you press enter, and then in parentheses, you just plug in the matrix that you want to find in reduced row echelon form. So you press second matrix. We type that into matrix A, so just press enter. Enter again. And it gives you another 3x4 matrix. And on the left side, we've got the identity matrix. That right column, 0.5, 0, negative 0.5, that would be our solution to this system of equations. If you don't want decimals, you can always press math and hit enter, enter, and it gives you them as fractions, 1/2, 0, negative 1/2. And so those three numbers would be the solution to this system of equations, right? Like if I plugged 1/2 in for x, 0 in for y, and negative 1/2 in for z, this would work. This first equation would equal 0. It would work for all of these, as a matter of fact. Did you get these three numbers? Okay. Good job. You did it right. I don't know what's wrong with my calculator. I did have a nicer graphing calculator app for the PC, but then they started charging money for it, which I did not have available. Like $150 for this program, and I didn't get it. So I found this default one, and it is not as good as I would like. I'm in the middle of getting a better one to demonstrate these to you. So sorry that this is not that great for now. But did everybody else get 8, negative 5, and 2? Great. Good job. You did it correctly. All right. What do you think? I mean, that's what I'm testing you on, right? I'm teaching you skills. I want you to demonstrate it. How do you get good at it? Well, you practice it. And we've got half an hour right now to practice. Okay? I've got nothing else to teach you. The rest of this class is just practice time. Okay? So, if you don't have your Chromebooks